So I'm a technical manager at XLam. I've been here for about 5 or 6 months now. And prior to that, I was at Wood Solutions working with Mid-Rise Advisory Partnership. So it's great to be back and part of this webinar series. So in today's topic, we'll be looking at something that I think is super important. Just for starters, when it comes to on-site performance and how quick our buildings go up in mass timber, we think about 80% of the issues come with tolerances when it comes to buildability. So it's something that we need to be focusing a lot of our energy and effort on. So it's a really important topic that we're covering today. So just at the very high level, some of the elements that we're going to be looking at is, first of all, is moisture. So when timber takes in moisture, it's a natural material. Obviously, that water has to go somewhere. So we do have volume changes within the timber, which is mean our building is going to move in certain directions. We've also got deformation, like any product, that when we squish something or we put load on something, depending on the stiffness of the product, it's actually going to deform to some extent. And thirdly, we look at manufacturing tolerances. So we've got some super accurate machinery with the CNC machine. So we do get within millimetre tolerances here, but it's something that needs to be allowed for in our design. We've got construction tolerances. So when we go on site, we're not using CNC machinery with the millimetre tolerances. There's humans actually assembling these pieces together, and in doing so, it's not going to be 100% perfect. We'll look at a case study, and then finally, we'll look at some of the connection solutions that we can look at adopting to overcome these tolerances issues we might have. So as a bit of context, before we zoom into the 100 feet level, we'll go at the 50,000 foot level and see what makes a successful mass timber building. So a lot of us have probably heard of the term and the phrase design for manufacture and assembly, which is DFMA. I'd like to just put in the letter T in there, because if we cover design for timber, manufacturing and assembly, we're going to be downhill skiing from there to have a really successful project. So firstly, designing for timber, from our experience, if we're designing with CLT specifically, spans up to 6 meters, we're really competitive with concrete. We can be shallower than concrete, and our floor to floors that we're used to will be achievable with CLT. When it comes to XLam, it's about to the 9 meter range we can get to. So designing with the material first is super critical, like understanding how concrete buildings work. We've got post-tension flat plate slabs going two-way action. It's a very different product we're working with than timber is. Secondly, avoiding load transfer. So we want to have simple load paths as possible as we go down the building. And also designing for one-way spanning systems. So as I said, concrete, it's typically a two-way spanning system where you can get, say, to 7-8 meter spans. When it comes to timber, if we're looking at it as a one-way system, we're going to have a reduction of elements and get the efficiency that we need. The second component is design for manufacture. So we typically prefer big panels as possible. If you think about if you've had IKEA experience in the past, if you've got this little bedside table that takes 6 hours to put together, just doesn't feel as efficient as you got big elements with as less connections as possible. And it's exactly the same when it comes to buildings. So for manufacturing, larger volume means less lifts inside the factory, less QA checks and so forth. It's also important to understand the tooling, so avoid creating bottlenecks at the CNC within the factory where we can, and avoid panel flipping. So, certain details mean we're going to actually flip every panel within the factory. And a lot of these costs will get passed on to our building. So if we can design in the right way for manufacturing, you're going to have a much more cost-efficient building up front. And finally, design for assembly. So this is a bit closer to what we're talking about today. So big panels, it pops up again because it is super important. So if we're, say, installing at a rate of 2 to 3 panels per hour, it might be quicker than that. If the meter's squared or the panels are really small, we're probably not going to be beating concrete. If we've got big panels, we're installing a large meter squared per hour, and that way we can be faster than concrete. And then we get all the cost savings that come from the reduction in prelims up front and so forth. Another element of design for assembly is replication of elements. So it's very normal that at the start of the installation procedure, there's a bit of learning going on. It's a little bit slower than the very end. So at the start, if you've got the same things to replicate, you're going to learn on the first few elements. And then as you go up, then you're going to literally be earning with the amount of speed that you're going to be installing with, because it can be rapid fast if we're designed with the replication. And finally, which is a bit close to what we're talking about today, is designing for tolerances and buildability. I mean, you don't want the panels to get to site and then things aren't fitting, and you might have some precast elements or some cast-ins, and then all of a sudden you're post-fixing everything and a lot of surprises on site. So this is what we want to be avoiding as much as possible. So what we're trying to do with our buildings is there's a range of different things. So we can be designing with other materials in mind. So designing, say, with steel, like exoskeletons, which is an exciting building going up in Sydney, which is the Atlassian Tower. Minimising hook time as much as possible. So as soon as the connection is in place, we can get the crane and lift the next element and not stay in there for too long. We're designing with other materials like concrete cores. So this is obviously very common, particularly as we get really tall buildings. Concrete cores are stiffer than CLT cores, and because of that, we can rely on concrete cores as much as we can. But there's going to, again, be different movement profiles and different tolerances with concrete. And, you know, unitized facades. So if we're trying to eliminate scaffolding and design with a fully prefabricated facade, we need all that to fit together almost perfectly, particularly when it comes to passive house design and everything fitting together in a really snug tight with a very small tolerance. So that's what we're trying to do and achieve, but some things can go wrong. Like the casting connections can be off the mark and it looks all nice for getting it all in the precast, but on site, you're just gonna have to post-fix again. Your panels change size unexpectedly, potentially. You got additional stresses applied to connections if the in-service movement is a bit different to in construction. If you're not looking at it, then plasterboard might crack if it's not designed for. Same with the services, might have additional steps throughout the buildings. So there's a range of different things that we have to keep in the back of the mind when we're designing for tolerances. So there's a few different cases that we can look at. So I briefly mentioned the different elements of movement. There's, I'd say, 4 different critical cases to check from a design point of view, an engineering point of view, which is going to be relevant to our installation, but also our in-service performance. So the first case, which is really related to this design for assembly we're talking about, is the in construction. So we want to know the plus or minus range that we're going to be installing our elements at. So there could be a plus case. So this is where some moisture might enter our timber elements, and there might be some expansion of our building, and there might be some swelling. So that means we're going to be above the mark with our CLT going on the plus end. But there's also the minus end. It might be shrinkage of CLT, and there might be a bit of creep. There might be some deflection from the transfer structure and so forth. And then in service, the 2 cases that are perhaps the most relevant is firstly, understanding case 1. So let's say if we install our building when there is moisture and swelling of our timber elements, we're going to be designing above. And then in service, in 5-10 years down the track, when the moisture content's going down and it's loaded up and you've got additional creep, we're going to have our in-service minus. So understanding the difference between what the worst case scenario it's installed at in terms of height versus as low as it could possibly get as well. Okay, so now zooming a bit more into moisture. So these are some of the equations we can look at. So the unit tangential movement to the grain is different for each species of timber. When it comes to radiata pine, which is what our CLT is made up of, and also a lot of glulam out there, it's 0.27. And the value is going to be different to floors and for walls. So if you think about how a tree evolves, it evolves with all the grains going in one direction, and it's designed to really take moisture from the top of the tree down through to the tree trunks. So when you get the moisture going through the parallel grain, so in the direction of our walls, there is much less movement than there is for floors. So floors, it's about 40 times as much movement per unit length. And as I was saying, timber is an anisotropic material, so it is different longitudinal to radial, and that's why it's different in our floors and our walls, because that's how our timber products are made up. So understanding this delta MC, so the change in moisture content, is really where it's at, and that's where we've got most of our control, and this is where all of our understanding really should be going towards to understanding our movement. So the life cycle of the moisture content, so let's say we've got our green timber, it goes into the kiln dryer as our feedstock. So as the kiln dried, it gets rid of most of the moisture up to a very predictable moisture content. From there, we lay up our CLT, and then we wrap it up. We put resin Lignagard on the end grain to protect it from moisture. So it's a limited amount of protection we can do in the factory. And then it's delivered to site at a predictable moisture content of about 12% plus or minus 2%. So then what happens next is super important. So, and this is what we do have a lot more control over on site, and a lot more focus needs to be in the design. So if you leave the panel out for too long on site, let's say there's a lockdown for a couple of weeks and people just leaving CLT on site because of that maybe, if the rain does come, then the moisture content will go up. So the water's got to go somewhere. And if you just let it seep into the CLT, it's going to enter, and then it might increase in its moisture content. And because of that, the volume can change. So a few weather events, it's not unrealistic to have, say, 3 to 4 millimeters of swelling within the CLT and CLT walls and floors in this case. So that's construction. So we might install it to whatever moisture content it might be. If we cover it up, there's different ways we can do the just-in-time installation to reduce or remove this risk. We can apply resin Lignagard to the face and the edges. We can make sure there's a serious moisture content control plan. I mean, we're just talking about tolerances today, but there's probably even bigger issues from a durability point of view if we're hitting 20% and above for the moisture content. So that's in construction. Then we got in service. So what happens after it's been installed 5 or 10 years down the track, or a bit sooner in this case? The moisture content's going to go in one direction. From there, typically, it's going to be going downwards. And this is going to be a function of the equilibrium moisture content, which is due to the relative humidity that the timber experiences when it's installed. So yeah, timber is a relative humidity of about 60 degrees, and say we humans like temperature about 22 degrees. So it's probably going to be about 10 to 12% typically, but you might have a more conservative assumption down to about 8% moisture content. And that's what we're going to be shrinking down to after it's been installed. So as it releases moisture, we're obviously going to be shrinking out our panels, but also our building. Okay, so that's all about moisture. Next, we're looking at axial deformation due to the Young's modulus of the product. So the E value and the general stiffness as it's loaded, and how much our building shrinks because of that. So as I was saying before, timber's evolved in the direction of where where the tree really needs its strength. So it's very stiff in that direction when we load it up. Trees aren't really evolved to be cut and then put on its side and then squished up in that direction. So because of that, we do have quite a stiff section when it comes to our walls. More attention needs to be paid to our floors. So this is the equation really to calculate the amount of movement. And of course, long-term creep factor is important here. In construction case, you wouldn't include this, but in service, at a worst case scenario, it might reach at about 2 for CLT. So as the load passes through our walls and starts going through our floors, the load can spread out. So typically you can get a 45-degree angle load spread to increase your bearing area here. So you'll have a reduction in your movement within the floor section. And it's going to, the Young's modulus is about 1/30 of it in the longitudinal direction. And if we follow the load path, so we mentioned the walls and the floors, and perhaps the most critical to think about is what's happening at our transfer slabs. Is our wall situated at mid-span of a transfer deck? We typically recommend designing the transfer to about span on 1,000 for a couple of reasons. One of them, if you think about it, for the relative stiffness, if we've got our very stiff wall element on a pretty flimsy transfer element, it's not necessarily going to be designed as a inflexure. The wall, it might be actually strutting down if the element below it's actually not stiff enough, and it's typically not designed like that. So we don't want load concentrations within our panels. So that's probably the primary reason we want span on 1,000. But also it just means that our building's going to move less. So when we're designing for span on 1,000, we're going to have this initial dead load deflection. So your construction case will be different to in service. So, and it might be pre-cambered. So again, understanding the nuance about in-service versus the construction case. All right, now, so manufacturing tolerances. So as I was saying, we've got this super accurate CNC machine as the billets go through to make up panels. Depending on the tools that we use to make the different cutouts, whatever they might be, there's going to be slightly different tolerance. On our spec, it's pretty much across the board, plus or minus 2 millimeters. And I'll soon explore the difference between bias and noise and looking at the difference of panel versus buildings. But I'd say this is the much higher end, is the plus or minus 2 mil. On average, what you can expect will be a bit much more accurate than that even. So the most critical ones we'll be looking at is perhaps within the floors. So this is going to be the thickness of our CLT, and looking at the processes, we've got a planer that planes our feedstock, and so it'll be based on the tolerance of that, plus the gluing and the pressing. And on our spec, we're going to be plus or minus 2 millimeters for the overall thickness of our CLT floor panels. But as a typical average, you're probably going to be on the higher side and probably on the 0 to 1 millimeter. So super accurate. But if it's very critical detail, you might want to assume the plus or minus 2 millimeters, which is perhaps the higher end. And similar with the length. So for this, we get a circular saw that trims around the edges of all our CLT. So the height of our wall is going to be based on the circular saw tolerances. So again, plus or minus 2 mil and up to 1 millimeters as your typical range. So it's slightly on the higher end, typically what we'd expect. And as a rule of thumb, if you're looking at all our tools, perhaps plus or minus 2 millimeters is something good to keep in mind. But again, it is a bit more accurate than that, but as a loose rule, that can work. All right, so now the final part of tolerance is installation tolerances. So as I was saying earlier, when you're trying to fit things together, you can't expect perfect accuracy from the installers on site. The installation tolerance is going to be very different based on what you might be installing. It might be a very snug tight naturally, or sometimes it might be harder to get that snug tight on site, and there might be a bit more movement, particularly if you've got multiple panels next to each other. You might accumulate as you go across. So there's a bit of nuance in installation tolerances, but we can help with some crude assumptions. So you might have, say, the alignments between two floors. So one floor, it might not be perfectly aligned. Same with walls, it might not have your perfect alignment when it's installed. So it might be within plus or minus 5 millimeters in this case. So these are just a few. There's a lot of different situations we can look at. You got the base of the wall panel, so you're not going to have that perfection. So this will obviously result in eccentricity as well that needs to be designed for. And you might have your story to story deviation from the top of the panel to the bottom as well, where again, it's not absolutely perfect. So this isn't unique to CLT and timber. It's also apparent in precast concrete as well, perhaps at a higher extent when it comes to precast concrete. And when we're installing our anchors, so one of our lessons learned, so over time we've had a lot of lessons learned as CLT becomes more mature in the market, but a few of them, one in particular, is really working closely with precast contractors and understanding that where, CLT manufacturers within plus or minus 1 or 2 millimeters in terms of manufacturing accuracy. Precast contractors are typically a bit looser because they've never really had to be more accurate. So it is extra bonus points if they're working in 3D and also paying a lot of attention through the whole process with them, the shop drawing process, and make sure they're aware of the accuracy we're going to. But anyway, you might have some crude assumptions about what you're looking for here, and that's cast in, but also in the post-fixing case. So you're not going to have that perfection when you post-fix something in. So when it comes to installation tolerances, I really recommend a resource, Trada National Structural Timber Spec, specifically on page 65 to page 73. It'll go through some different assumptions that you can have when it comes to installation and the different cases you might have. All right, so now looking at adding them together. So it's where it gets quite different is understanding the tolerances when you're installing one specific panel, because let's say in the construction case, all we care about is really where that panel is relative to where the connection is. So with that, we might assume for individual elements a worst case scenario of everything to go together. But as we go up in a building, if we're assuming every connection to be worst case scenario, then our building is going to be overly conservative, and some of our assumed movement and tolerances might end up a little bit silly. So there's one important concept to keep in mind, and it's the difference in understanding what parts of tolerance are noisy and which parts are biased. So this is a term coined by Daniel Kahneman, who won a Nobel Prize in behavioral economics, but so this is applying to a different context. But let's say if you've got a AFL football, let's say Max King kicking goals at the full forward. Let's say one day he kicks a bunch to the left hand side and then the right hand side behind. It's going to be noisy. So not many going straight through the middle. On average, it's straight through the middle, but there is error with every single kick. Secondly, let's say if he's kicking goals with one boot on, let's say he's forgot to put his right shoe on and he starts kicking goals, and then everything veers to the right. So that's going to be biased because it's the same amount of behinds, but it's all going to the right-hand side. And then sometimes you might be missing with the right-hand shoe, but also kicking all over the place. So this is really important when it comes to understanding tolerances and how much we stack them as we go up the building. So some noisy elements, let's say if you're installing panels on site and there's rain one day, it's unlikely to have rain every single day at every single level to be accounted for. So if you assume, say, it went up to 20% moisture content, that might be overly conservative. So that's perhaps a noisy element. There's some parts that are a bit more biased. So deformation is something that it's predictable, and as we load up the building, we're going to have it within every level. What we deliver the moisture content at, it's going to be biased. So I did say plus or minus 2% from 12%, but you know, if it's say the middle of summer and our feedstock was taken from at the same time, they're all going to be probably on the higher end or the lower end consistently of that 12%. Then some parts are biased and noise. So as I said, manufacturing, it's probably going to be closer to plus, so 0 to plus 1 millimeter when it comes to manufacturing and installation, depending on what you're installing. So this can be super critical when we actually add them all up together as we go up the building. What's also important is understanding the differences in movement for different types of buildings. So posts and beams, so if we don't have much perpendicular grain loads, then there's going to be much more moisture, which is going to be critical for where our movement actually happens. So that's the case in post and beam buildings. When we go into light frame buildings, we're going to have highly concentrated loads with studs going through, say, plates and whatnot, and squishing our perpendicular grain. So there's going to be more deformation in light frame buildings, and typically it's going to be a function of moisture for CLT buildings. So I'll get through this slightly on the quick side. So number one, the first thing we need to do is make assumptions. So what's the moisture? Have a chat to the installer and the builder. What moisture content can we assume it's going to get to? Do we have a moisture content plan to control it? Where's our transfer structure? Are we at the midspan of it? And how much deformation can we assume here? And depending on what we're installing, what's our construction tolerances? So we've got the plus or minus construction, but similar for in-service. And when we add it together, these are the sort of numbers we look at. So there could be a worst case scenario, and this is where it's a bit more art than science, because it's a range where it's a lot of uncertainty. So say at level 4 in this case, adding it all together with the assumptions I had in the previous screen. So level 4 would be plus 40 to say, you know, minus 40 around that. That might be your range at your worst case scenario. But again, you're perhaps going to halve that and might be within plus or minus 20 millimeters as a best guess. And then in service, so what's our worst case for our plus installation, and then installing it when our building's expanded and swelled up, versus in service, what happens later down the track. And now Rohan's going to cover a few of the connections a bit more in detail, but there's a few things we can do. So there's Orbi plate connectors. So with this, it can give you some movement within the plate with ferrules. And if you install, say, 2 Orbi plate connectors with 2 ferrules above each other, 40 mil apart, you can say get with 80 millimeter range. So with that, you can allow for tolerances with concrete, for example. And you can also look at site welding. So particularly as you get much bigger buildings and there's much more movement in our buildings, you might look at welding plates together to allow for your on-site tolerances before you connect whatever connection might be for your meg amps or whatnot. So there's a few things you can look at, and appreciate everyone for your time today and look forward to answering your questions. And I'll pass it over to yourself, Rohan.
Thank you, Adam. And everyone, welcome again. Thank you for your time. So today we'll be talking, I'll be talking about the tolerances, pre-assembled elements, handling of movement and material and protection from a installation point of view. So what we can do, how we can bring our input. So with tolerances, I'm going to discuss the processes that I go through to design a successful connection for the buildability aspect for the on-site installation. The pre-assembled elements, so what can be pre-assembled? Where can they be pre-assembled? Can we change connections? Can we change things to be pre-assembled? Also looking at elements that aren't typically or aren't known to be a pre-assembled element that get missed a little bit. Handling and movement of materials, so the different techniques of moving some of the mass timber materials. I'll probably talk mainly about the CLT parts there, and protection, just different elements we can protect. If we've got enough time, we'll go through that a bit more, mainly just in regards to damage of protection. A couple of quick, just a bit of that background on Savcon before we get into it. A couple of projects or projects we've done. The world's largest mass timber project by volume, we've completed in Singapore. Most recently, we're finishing up Batemans Bay Aquatic Centre now. The Q building in Newcastle, where a webinar was done a couple of weeks ago. Quite a good case study that I'll be utilising a couple of photos on that today, and Macquarie University in Sydney here. So the Mac Uni building, post and beam structure. The tolerances that we came up here against were obviously the concrete structure. We had the V columns at the front of the building there that were on concrete plinths. We had a couple of structural steel elements also to bring in. So the fair bit of tolerances to bring in on that ground floor slab connection. And also the column to beam connections were a Sherpa connection. So the lessons learnt from this project that we had with the Sherpa connection actually didn't come pre-installed on the element onto the beams or the columns. So it was like I said, a good lessons learned for us and the builder to really understand the level of impact it has on the speed of us installing those Sherpa connections on site. Honeysuckle, as I discussed, was a webinar the other day or the other week. Great project, a small little project as it is, but had a lot of different challenges that were quite successful. We were able to be engaged early enough to be able to bring all these different types of methodologies, how we can value add to these connection types and make it a successful project for all. This will be one of our major case studies today that I talk through. The Granville Park Stadium, this was just a GLT structure, had a 8.5 metre long cantilever at the front, so the tolerances were extremely critical to make sure that cantilevered beam didn't deflect more than designed. That was another great one that we were part of. And the most important one, or most recent one, I'll say, was the Batemans Bay Aquatic Centre. As you can see, that bottom right-hand photo there was a 33 metre long bowstring truss. All the splice connections were pre-installed, but not every element can be pre-installed. Those droppers and the tie rods just cannot be pre-installed due to shipping. But going into now a bit more about the individual things, so the tolerances. So the questions that I always ask is quite a basic one of what are the known and unknown tolerances between the elements, and how do we design the connections to accommodate these tolerances? So I'll go through these 5 different types of connections. There are many more. But the first one's probably the easiest to understand my simple questions and how we go through and break it down and make it a successful one. So a GLT column base plate connecting to a concrete slab. So what are the known tolerances? What are the unknown tolerances? And how do we design this connection? So a known tolerance is going to be the actual column itself. We know the length or we know the RL it should be at. And what are the unknown tolerances? So if we're going to an existing concrete slab, we can go and survey that and change that unknown tolerance to a known tolerance. But if we, more often than not, it's going to be a new concrete slab and we're designing this building 3 months in advance and we don't know that. So we can have an educated guess, but we've got to build in those tolerances because the glue lamp column is going to come millimetre perfect and the concrete slab could be out 5 or 10 mil or more. So this is quite an easy one, like I said, but understands the mindset of how we do it. We just design in a grout zone. This could be 10, could be 20, could be 50 mil, depending on all those unknown tolerances. So it's that's where we can design in that tolerance on site, so we can continue with manufacturing of the GLT columns and have a successful connection. So another one is, next topic tolerance we're talking about is a GLT column to beam or a CLT panel. So this is, what are the known unknown tolerances? They're generally all known in this case. We know the lengths of the GLT beams, as Adam just said, are generally within 2 mil, more assumed to be within 1 mil, and the same with the CLT panels. So knowing that, but we still don't design them to be a zero tolerance connection between the column and beam. We still might add in a 2 mil connection between the column and beam connection. Between CLT panels, we might add a 4 mil connection to make sure we don't constantly grow the building with these tolerances. We have room to pull that building back in. The more difficult ones is going to be a GLT beam to a concrete wall. So this is where you're going to have a core wall, could be a tilt up, could be an in situ concrete structure. It could even be another one, could even be a structural steel wall or another element. But this comes up quite common because the concrete core generally gives you that robustness or stiffness, that diaphragm to build off. How do we get it? Because sometimes that core is in the center of the building. So we have the timber structure going all 4 sides of it in that east, north, south, east, west direction. Sometimes only in 3 sides. So when you have that, you might have, if that core is out by 10 or 20 mil in a north direction, you're also now out that 10 or 20 mil out in the south direction. So in one case, you're going to be shortening up a gap, and in the other case, you're going to be elongating the gap. So it's how do you build this tolerance to be a 2-way tolerance now, both a positive and a negative case. So this one was done at the Q's building or the Honeysuckle building. We did that. It was a very successful connection. We had to keep the GLT member designed, had to get it fabricated, like I said, 3 months in advance because it comes over from Europe with a steel plate already installed, which is that bottom left-hand corner there. And we had to have a system that can be done on site to bring up that tolerance when we go and build that structure. It might only be 2 weeks prior to us installing this beam. So the way that we did that is that we had that on-site weld. So we went there, we cast in the cast-in plates, which can be out of tolerance in an up, down, left to right, or even out of pitch direction. We cast that in, had a survey mark, and then custom made that thin plate and welded it on site. That took all those tolerances out. So on both the negative case and also the positive case, so on one side of the core and the other side of the core, that took up those tolerances. That's quite a tough detail to get right, but a very successful connection. A similar one is the CLT panel to a concrete wall. So a similar type of connection we just talked about, but obviously not with the GLT member, with a CLT member. A slightly easier one, generally you have a ledger beam or a shelf angle. In this case, it was a ledger beam. It's much easier to go here. More often than not, we know the tolerances of we do know the tolerances of the CLT beam. Again, we don't know the exact tolerances of the core structure. But if we go for a post-fix option here, we can go with the Orbisorb plates that Adam was talking about before, but that can bring in that up and down tolerance. So we can eliminate the up-down tolerance or the height tolerance here because we're going for a post-fix shelf angle or ledger beam. And if that CLT panel was cut short, designed to be cut short, 10 or 20 mil, maybe not 20 mil, maybe 10 mil, that's where we can bring that in and out tolerance of that core wall. So it's about knowing what are the unknown tolerances? So we can sit down with the other contractor, if it's the tilt-up concrete installer, and say, what are your tolerances going to be? And they can say, our general tolerance is 5 and 10 mil. We can then go and design those into these connections where the tolerances don't align. Just going through the next one. So pre-assembled elements. So what elements can be pre-installed? Where can we design to maximize pre-assembly, and what are the advantages of pre-assembled elements? So we'll go through 3 connection types here of pre-assembled elements. So the first one is can't always assume that you can pre-assemble every single element. This is a GLT base plate. The photo was just before, and we could not pre-install this element because the base plate was the same size as the GLT column. The anchor bolts are actually recessed inside the column. It was extremely hard to, you can see why you can't pre-assemble that. An option is, if you can, is to pull those anchor bolts outside the line of the column. So this element now, if we were to change the base connection to this type, we can pre-install that shoe, and you can see by the vast number of screws or bolts, stainless steel bolts that are in that connection, the speed on site that we'll be picking up. And generally those bolts get covered by the finished floor level, mimicking that line there, so they get concealed. Pre-assembled elements, another one here is a GLT column to beam connection. Very, very common in all post and beam connections. This one probably a bit easier for everyone to interpret how we can pre-assemble these. Going towards maybe a Sherpa or a Megant or any of those slip connections, it is a bit difficult to pre-assemble the Rothenblast alley maxis or midis because they do stick out and transport can be an issue. With a slip connector like this, you can see transportation doesn't really get impeded by having these installed, and you can see by that bottom right-hand photo the sheer number of screws that have been saved on site. So it's quite important when you're talking about something about these screws. The time what has a benefit to us on site? It's the time on site. So that's your no-brainer by how long it's going to take to put those. It's also the double movement of materials. So if that's already pre-installed, we can lift that straight off the truck or straight off the pile and install it straight away, opposed to taking it off, putting it onto a trestle, and then pre-installing, then installing those screws, and then taking it from that trestle back to the installation. So there's multiple facets why pre-assembly is important. So that was a Megant connection there. Lifting systems. This one gets overlooked a lot. This one, because it's not so much a structural design, it's they talk about panel sizes, they talk about screw connections, you talk about connecting and post to beam connections. You very rarely talk about, as a design talk, about how do we lift the CLT members. This is one of the ones that constantly gets missed, and we normally miss the boat by the time the installer gets engaged about having an input into the lifting methodologies. So there are many types of them. We'll talk a bit more about the different types of lifting techniques with CLT panels in a couple more slides, but all of them can be pre-installed. If it's slings, you can pre-install slings. If it's the wasps here, you can pre-install the screws. If it's a ramper, they can pre-install the insert. Again, this speeds up time on site, also limits safety. So if a person was trying to install these wasps or install these screws on site, and they might install the wrong screw or they might install the wrong sling, it can have a safety consequence. So the advantages of pre-assembled elements, it's clear, it's speed on site. So we can take that time off site, put into a factory, a more controlled environment. It's going to be quicker, and it's going to end up costing less. The ones that are less known or less obvious sometimes is less movement of materials. So like I talked about with that Megant connection or the Sherpa connection, you don't need to then double or triple move materials. The less movement of materials becomes less damage, less repairs, and then required less space. So if we need to double handle these and put them onto trestles, we obviously need more space to do that on site. So sometimes space on site is limited. So trying to take all that work off site into a factory, we can then install the back of a truck or have require less space on site. So handling and movement of materials. So what elements are going to be handled and what options do we have for these? Like I said, I'll talk just about the CLT panels because that's probably the trickiest one. The columns and beams are pretty typical. Columns we generally try and put a 40mm hole through the top of the column and lift it, and the beams we generally use conventional slings. So lifting CLT panels, walls or floors, This photo here has like a yoke connection. It's like a screw fix connection. So it's a steel plate that gets screwed in on site. Personally, we don't really like these. It's just time. It goes back to those plates need to be screwed in on site and then uninstalled, taken back down to the crane, and then reinstalled again and circulated. You might have multiple sets of them, but that process constantly happens. So the options that I'll be talking about are slings, the lifting hooks and clutches, and rampers and other types of it. So there's the photos there of slings. The middle one there is the lifting clutch and the ramper. When do we use each, or when would I suggest each? And why do I use them? The slings are the easiest and most conventional one. So everyone knows them. If you give that sling to a dogman or a rig or anyone, they know how to use it. It's the easiest, simplest one to use. Where we use it is when, say, a Savcon, say a CLT panel, a floor panel, if there was a plasterboard going under on the Savcon and it's not exposed, I'll go for the sling option because you don't see the actual holes that are plugged. Generally, slings have a through hole through, the sling option has a through hole through the panels, which will need to be plugged for fire rating. But if it's an exposed Savcon, you don't want to be looking up and seeing all these plug holes. So that's when we go for more of the lifting clutches or the rampers, whether an insert screw or an insert thread, and we can go from a on-top type of a CLT connection, and it limits the plugs. So there are two types. They are a bit harder to use if people haven't used them before. They might get a little bit hesitant on using them, where the slings, I said, it is foolproof. And the last one that I'll talk through here is protection. There's plenty of protection. We could talk a whole webinar about protection. We could talk about UV, UV damage. We could talk about water damage. If the list goes on and on. I'll talk about physical damage because it's probably the most costly in the sense of if something goes wrong, repairing it. Most defects come from this, and it's probably the easiest one to solve. So what elements can get damaged? Most of the time it's the columns. Very rarely do beams get damaged post-installation, and CLT panels, again, very rarely do they get damaged post-install. So it's generally the corners of the columns or the elements that get damaged. They get damaged from just general site traffic, could be from site toolboxes, ladders, movement of materials, anything like that that can damage it. So you can see it's always, or not always, but it's generally around the edges of the column. So a simple, very simple solution, which is quite cost efficient, is putting plywood protection around the columns. It has that initial impact that gets chipped away, and then at the end of the project, when you take that away, you're still left with a lovely column. That's pretty much all me. I hope that gives you some insight onto our installation time and handling and speeding construction. So thank you very much.
Thanks for that, Rohan. All right, well, we've certainly got time for some questions and answers, so that's great. We've had a number of questions come up today. Might just start off with one for you, Adam, from Lisa. She was just asking about the different EMCs and moisture transfer in a panel, especially if there's been some construction wetting and the EMC might have gone up to around 15% or more. What do you recommend to avoid stress concentrations from drying stresses when this panel starts to dry back down? Is there anything you can do there?
Yeah, so I'd say it's just something that you need to design for, like any material, no difference in multi-story concrete buildings. Just understand how much it's going to move and make sure we're doing that within the connections. And also look at how we do our panel breakups. So you got sort of like a ramp, and as rather than having, say, continuous panel connecting into the core where you have additional stress, you can actually look at making sure the panel breakup suits to allow for that additional movement to take away the concentrated stress from the connections. Look at slotted holes, and like anything, it's just something we need to understand how much movement is going to be up front and design for it accordingly.
Yeah. And when you were chatting about particularly the CNC, and you mentioned about sort of flipping the panels, question asks about the floor panels with half lap joints require flipping during manufacturing, or can they be manufactured without flipping?
Yeah, so it depends on the thickness of the CLT panel. So what it's actually limited by is we've got the slab cutter, which is like a circular router, and it's got a head on it. So the base there, so the head kind of can hit the CLT panel, which is what we're limited by with our half laps. So if it's above a certain thickness, it can get a bit more difficult to do the half lap joint. So, and if that is the case, we might have to look at panel flipping. But, 99% of the time, we don't have to flip panels for that case. You can look at doing a spline joint connection. So we'd probably, if we had the panel flipped for doing a half lap, we'd look at doing a spline joint detail instead to avoid flipping altogether.
Thanks, Adam. Rohan, a question here from Jeremy, which is an important one. He's just asking if the timber manufacturers pre-install in the connections prior to shipment, and what's the approval process confirming they've been installed as specified?
Yes, all timber manufacturers pre-installed all those connection types prior to shipment, if it's a connection plate or if it's a lifting system. The approval process is just pretty much like a stat deck saying they have installed it as per the specified requirements. Adam, did you have sorry to throw you in here, the ramper connections, I know that's an XLam preferred system. Is that what you do as well? Just, issue a letterhead saying that you've installed as per the manufacturer's requirement?
Yeah, absolutely. Like that. If, ramper connections, if we're going for exposed panels, but also drilling holes for lifting slings if with plugging afterwards. So we would issue something like that.
Yeah, I'm guessing with your slings as well, would to answer that question, Alistair, would also they'll be tagged lifting slings. So yeah, it's not so much a approval process, it's just more of a document saying they've installed as per the manufacturer's requirement.
Yep, thanks for that. Adam, a question just on the moisture content of CLT. Does that go up if it's not in contact with rain, so it's just out in the sort of ambient sort of temperature, the humidity, will that pick up moisture, or is it not such a big issue?
No, not really. Not in the short term. Like it's, as I said, in service, you don't have the rain, so it's a function of the equilibrium moisture content and the relative humidity. But like in the short term case, for in construction, that's not really going to mean much. So yeah, short answer, it's really going to be the weather and rain that it gets in there, which we need to account for. And again, as I was saying, the end grain, the edge grain being the most critical parts to look out for compared to the face of the panels. So yeah, all about the weather.
Yep. And a question here.
Sorry, I might extend on that, Alistair. And also, probably one thing with it can actually go the other way. If you say you're prefabricating, say, modular systems, and you're leaving your panel inside a factory or a container or something like that, and there's sun going onto it, it could actually turn into a bit of an oven where you actually get a really dry panel. So I guess I've been talking a lot about wetting, but there is a certain case where you can have a lot of drying. And in particular for our thinner panels, so say our 3-layer panels, we've had some cases where there can be bowing, despite we have dimensional stability with CLT. So say a 3-layer panels, we've got a really not so stiff in the secondary direction. If the moisture changes too much, we might have some distortions that we need to be looking out for as well.
Thanks, Adam. Rohan, on one of your slides there, when you were talking about sort of lifting panels, you showed the slings, which is a really easy way to do it. And the picture sort of showed a sort of hole bored through the panel. Question asked there, particularly when use of CLT for passive house type buildings, which we're getting. What do you do about patching those holes afterwards so you don't have a sort of air problem?
Yeah, so there's generally XLam will generally supply plugs for that application, or the manufacturer would do it. So you plug both sides, you might plug it, and then you might foam fill. If it's a larger panel, so if it's a 240 mil wide panel, you plug fill, you foam fill in the middle of the panel, and then plug fill the top as well. So it's a full system. It's not just a 10 mil plug fill.
Yep. And look, a good question here. Who's responsible for reworks on site when there are issues with tolerances? How do you deal with that one?
That's a tough one. So the reworks, obviously, if it's a damage caused from installation or an installation error regarding the reworks, then it's obviously on us. If it's a design error, then it's obviously to the drawing board and find out where the error came from and who's going to be doing it. If it's I think it's a hard one to answer. There's too many unknowns.
Yeah, absolutely. Typically from our end, I mean, we've got responsibility up till it's delivered to site, and then from that point, what happens, we can't really control how it's handled from there. So, yeah, we're typically pretty reasonable with builders and installers to work something out if something goes wrong. But definitely up until the point of delivery, where you would be fully responsible as suppliers.
Mm-hmm. Just back on moisture, a question from Adrian about, would you ever consider sort of painting and sealing the panel sides to prevent moisture ingress? Would that ever be a sort of problem or a thing you'd do?
Yeah, we would put resin Lignagard on the end grain. So we would deliver it with that in, but you'd also, if it's going to be out for the weather for an extended period of time, I think it gets you 3 months protection. But it'll just hold it there. So if it just ponds up and you just don't do anything about it, it will still find a way in. But you can look at putting it on the face as well as the end grain to just get you that extra bit of protection on site. But yeah, like you see in Europe, how seriously some of them take it, building tents over buildings to get the moisture right. So it's definitely something that needs to be considered up front and not really appropriate to be seen as just a quick little afterthought. So yeah, good question.
I've got a good question here from Paul, just on the concept of BIM and building information modelling and how that important that is. What's your thoughts, Rohan, there on the importance of having the installer involved in the design and or BIM process, particularly around the connections?
Yeah, critical. And that was one of the biggest successes we had at the Q building in Honeysuckle. We were engaged early on to be able to go through that design process and be able to put in our buildability concerns and processes into the actual design. So we can't change a connection if it's not structurally sound, but we might be able to twist or change or alter a connection detail to make it a successful connection on site. So yeah, it is quite important that you get the installer throughout that roundtable meeting with the manufacturer, with the structural engineer, and with the builder and also the architect to make sure it makes everyone gets a good tick. But yeah, very important.
Yeah, I'll just add to that, like Rohan's absolutely right. There's so many lessons Savcon's learned in installing so many buildings, and it's so important to get that right up front because, yeah, minimising the hook time and having as much speed is really critical for the project. If 80% of the time it's the costs and trying to get that speed of construction, and yeah, having the installer there is super critical.
We're almost out of time. Just a couple of questions to finish off to both of you. So Rohan, from your perspective, what do you see if you were talking to designers like we've got on today, what are the key things they need to be sort of thinking about with tolerances? Like which are the really key ones they just need to get right from your perspective?
I'll probably follow a bit more on tolerances. It's just getting the connections right. So understanding there's many ways to skin a cat, but it's just choosing the right type of connector for the right application. So if it's a smaller job, probably it's not as critical. But if it's a larger job, one small, getting the incorrect connector and times that by 1,000 types on a large project. That's probably one of the biggest ones. Is just choosing the right connector for the right application, which has those connections and fallback. So it's a open-ended question there, an open-ended answer. But I'll just say the connections between, say, post and beams, or between CLT, the timber-to-timber connection.
And sort of a similar question to you, Adam, from that design point of view, but particularly with your CLT manufacturer, what do you see are the critical things that designers really need to know?
Yeah, I'd add to that connections comment from Rohan, but also just understanding going for the replication as much as possible. It's got loads of different benefits. It's obviously much easier to manufacture, much easier to install. Your compliance pathway, let's say a lot of the time the amount of fire testing we've got over time has built up to, we don't necessarily need fire testing as much, but if you don't have as many different connection types, it's more likely that fire testing will be minimized or completely eliminated. So yeah, putting all the focus in connections, that's where most of the design energy goes. Probably 80% of the design is in connections, not just the design of elements. That's pretty straightforward stuff. So yeah, looking at that, and in particular the replication as much as possible.
Well, thank you both. It's been a fantastic webinar. It's a really important topic for people to get this right, and we really appreciate all your great knowledge that you provided there. So on behalf of everyone, thank you very much. To everyone in the audience, I just remind you that these webinars are recorded, so you can go back and re-look at them or sort of recommend them on to your colleagues, and we have a wide range of episodes there. So if you've missed some of the past ones, go and have a look at them. There's some fantastic webinars in the series. The next webinar is in 2 weeks' time, so the 12th of October. And just note, this one is actually going to be at 3 in the afternoon. So this is unusual. We normally hold them regularly at 11. But our presenter, Stefan Zollig, will be presenting directly from Switzerland. So at 11 o'clock, it's about 3 in the morning there. So that's a little bit late. But this will be a really sort of interesting presentation on timber structures and the revolutionary mass timber building systems that they're involved in. So we encourage you to register for that one. So thank you everyone once again for joining us. It's been another great presentation, and we look forward to seeing you again in a fortnight.